Hi, welcome to Chapter C on Galaxies. In part one of this lecture, we will be looking at our home galaxy, the Milky Way galaxy. So let's start by defining what a galaxy is. A galaxy is a huge star system that contains up to several hundred billion stars. So this is a picture of a nearby neighboring galaxy. I took this picture with my camera and telescope, and it looks sort of like a big swirling cloud, hazy cloud, and what we're seeing here is basically the stars are so far away and close together in this image that we don't see the individual stars. We just sort of see a haze of stars because there are several hundred billion stars. By the way, all these other stars in the picture that you see are actually stars in our own Milky Way, and we're looking out of our galaxy to see a galaxy like this one, which is called the Andromeda Galaxy. But in this chapter, or at least this part of the chapter, we're going to be focusing on our own Milky Way galaxy. So let's take a look at our Milky Way galaxy. First of all, it's easily seen on dark moonless nights when you're away from city lights. So this would be a bucket list item to do before you leave this Earth, basically, is get a chance to see our Milky Way galaxy. It's really an awesome sight. So get away from the light pollution of the city, go out to the desert or the mountains, maybe on a camping trip, and go on a clear night when there's no moon in the sky. You have to go during the right phase of the moon so that the sky is absolutely dark, and you'll see a sight that's just amazing, especially if you go in the summer or in the fall when you see the summer Milky Way overhead. So what does the Milky Way look like? Well, it appears as a band of cloudy light stretching across the entire sky. This is why the ancients called it the Milky Way. This is our home galaxy. We're living inside of this galaxy. So it contains more than 200 billion stars, most of which are probably contain multiple planets. So think of all of these stars like our sun. The Milky Way is a great spiral galaxy, a huge disk-shaped cloud of stars and gas over 75,000 light years across. So if you do get a chance to get out and see the dark sky sometime, this is what the Milky Way would probably look like to your unaided eye without a telescope or without any binoculars. This picture here was taken from our Anza Borrego Desert, which is here in San Diego County. So it's about a 2-hour drive east, and you're out in the desert away from the city lights, and this is the kind of sky that you can enjoy out there. So what does our Milky Way galaxy actually look like? Well, this was a tough puzzle and sort of a mystery for astronomers. It wasn't easy to determine the shape. They basically had to map out distances and locations and angles of all the objects in our Milky Way and try to put together a model. But now we have a pretty good feeling of what our Milky Way actually looks like. If we were to go outside of our galaxy in, let's say, in an imaginary spaceship that could take us far, far away very quickly. From the outside, our Milky Way might look something like this galaxy here. This one here is called NGC 7331. That's just a non-descriptive catalog number, but this galaxy is thought to have characteristics similar to our own galaxy. So our own Milky Way probably looks something like this galaxy here. So here are a couple of diagrams that will help illustrate the structure of our Milky Way. So if we look at our Milky Way face on, because it's sort of it's a flat disc-shaped object, then we get to see the disc here, which includes the spiral arms. Okay, you can kind of see how it looks sort of like a pinwheel here. And in the center of the disk is the nucleus of our galaxy. That's called the nuclear bulge. And you can see that more easily down here. This is a view view of our galaxy, or a diagram of our galaxy, edge on, looking at it from the side. So it looks kind of like maybe a fried egg, and the yolk is the nuclear bulge in the center. Now, our sun resides right here on the edge of one of these spiral arms out here in the disk. So from the side, you can see our sun is located right here. We're sort of out in the outer reaches of the galaxy's disk. One other structure I'd like to point out here, there is what's called a halo around the galaxy. It's sort of a spherical halo, and the halo we'll see contains some star clusters and some gas, and also something more exotic called dark matter. So this is just a little more detail on the structure of our Milky Way. So again, the main features are the disk, the nuclear bulge, and the halo. This is a nice, beautiful photograph of another galaxy taken by a professional observatory telescope, and probably could be the Hubble Space Telescope. And it shows all these features very nicely. So the disk, right, that's the flat part of the galaxy out here, contains spiral arms of gas, dust, and stars. And in the disk here, this is where new stars are forming. And the reason we know that is, look at the color. You can see the bright, the bluish color, and those are the bright O and B type stars, which are blue and are very bright also. And so they kind of dominate the starlight coming out of the disk. So that's why the disks of spiral galaxies appear as kind of bluish color. And of course, this is also where our sun resides. In the center here is the nuclear bulge, which is a dense cloud of stars around the center of the galaxy. It turns out there's not much gas and dust right in the center, so there's little star formation. Remember that stars form from gas and dust clouds. So without new stars forming in the bulge here, the stars that are there are older, cooler, and more reddish stars. So that gives the bulge, the nuclear bulge of the galaxy here, sort of a yellowish, reddish color compared to the blue disk here. And then around the outside is the halo, which you really don't see in this picture here, a spherical cloud of thinly scattered stars. It also contains globular clusters, and these are older, cooler stars. Here are a couple more examples of galaxies that are somewhat similar to our Milky Way. And so again, this gives us an idea of what our Milky Way galaxy might actually look like from outside of it. The Sombrero Galaxy, it's called, because it looks like the hat here. You can see the disk here, and you can see the nuclear bulge very well. And you can also kind of see this fog, kind of fuzzy halo surrounding the galaxy here. So this is a spiral galaxy like our own, seen edge on. And notice this dark, what's called a dust lane or dust band that cuts right through the galaxy. That dust, that thick dust and gas, is blocking the starlight behind it, so that's why it appears dark when we see it edge on. If we see a spiral galaxy face on, like this one here, this is NGC 2997, we get to see the full extent of the disk here and the beautiful spiral arms that wrap around the nuclear bulge in the center here. Let's now turn to some of the dynamics of our Milky Way. So the Milky Way, remember, is a collection of hundreds of billions of stars, and the reason they're all basically together to form a galaxy is because of gravity. They're all held together by gravity, and so basically all of the stars in our Milky Way galaxy are orbiting around the center of the galaxy. And so this is a computer simulation tool here that shows a spiral galaxy, and it shows the rotation of the stars going around the core of the galaxy here. So you can see, you know, every one of these little tiny dots here represents a star, and it's modeled by a computer program. There's also 3 bright stars that are shown here that are kind of like markers, so they're a little easier to see and watch. So there's a couple of interesting things about this. First of all, you can see the spiral arms where the stars appear to be more dense. It turns out that basically those are just brighter stars because there's star formation occurring in those spiral arms. But let's take a look at the rotation of our 3 marker stars here. Notice how this one here, closest to the center, is going around the galaxy the fastest, and this one out here, which is farthest away, is going around the galaxy and orbiting the galaxy the slowest. Well, this is just Kepler's law again. Remember with the planets, planet Mercury goes around our sun very fast, Pluto goes very slowly because of the distance, and there's less gravity out here. So we see the same thing with a galaxy. The galaxy, all the objects or all the stars in a galaxy rotate differentially. What that means is the galaxy doesn't rotate as a solid object like a frisbee would. Instead, it's a bunch of individual objects all rotating or revolving or orbiting independently. And so the closer you are to the center, this galaxy is going the other direction in this picture, but a star here is going to go faster than, let's say, our sun, which is right here, and a star outside of the orbit of our sun is going to rotate around even more slowly. And everything is rotating around the galactic center. So for our sun, is orbiting around the galactic center at 220 kilometers per second. Now that's about 500,000 miles per hour. So that's 500,000 miles per hour. So think about what that means. Our solar system right now, including us, we are orbiting the center of our galaxy at 1/2 of a million miles per hour. So that's how fast we're actually moving through our galaxy right now. And of course, we don't feel or notice that speed because there's basically very little acceleration, and we can only detect acceleration. We can't feel velocity. One orbit of our sun takes about 240 million years to make one trip around our galaxy. Even though we're moving this fast, the galaxy is obviously enormous, so it takes a long, long time, 250 million years for our sun to go around once. And we talked about the differential rotation here, how stars closer to the center go faster and stars farther out orbit more slowly. So how massive is our galaxy? How much does our galaxy weigh? Well, you know, this is another one of those things that we can't determine directly. We don't have the ability to put our galaxy on a scale and weigh it, obviously. So we have to determine the mass through indirect means. And so there's a clever way of doing this, which we won't be concerned with the details in this course. But basically, what astronomers do is they look at the motion of the orbits of stars around the galaxy, and they apply this to the laws of physics, including Kepler's laws, and they can determine the mass of the galaxy, which is causing that orbital rotation. So by doing this, they come up with an approximate mass of our Milky Way galaxy is about 1 trillion suns. 1 trillion solar masses. But here's the very puzzling and mysterious thing about this number. Only about 1/5 of that, or 20%, is due to stuff we can see, like stars, gas, dust, and planets. That means that 4/5 of the galaxy, 80% of our galaxy, is invisible and unknown. So think about another way to think of this. Imagine, let's say I weigh about 200 pounds. And one morning I get on the scale, and the scale says I weigh 1,000 pounds. All right? I'm 5 times heavier than I should be. So I look in the mirror, And well, first of all, maybe I look at the scale and say, okay, something's wrong with this scale. But no, I put something else in the scale and it weighs exactly, what it should. So the scale is telling me that I weigh 1,000 pounds. So the next thing I do is look in the mirror and like, what happened to me? Did I turn into the Hulk or something? But I look in the mirror and no, I look exactly the same. So why do I weigh 5 times more than how I look? There must be something invisible, about me that I can't see. This is exactly what's going on when we look at the mass of galaxies. Galaxies weigh about 5 times more than they should. There is something there that we can't see. It's not stars, it's not gas, it's not dust, it's not planets. We don't know what it is. We call it dark matter because it is not giving off any light. So let's take a look at this in a little more detail. So dark matter, again, the mass of a galaxy is usually much, much larger than what we can see, sometimes 5 times larger. What is and where is all this missing mass? Well, we don't know. So we call it dark matter. It's a mysterious substance. It does not absorb, scatter, or emit light. That's why it's called dark. It's basically immune to light or electromagnetic radiation. However, whatever this stuff is, it does contain mass. Okay, it's substance, and it acts as a source of gravity. Remember, gravity comes from mass. So this dark matter increases the gravitational forces of the galaxy, causing the stars to rotate faster and so forth, but we can't see it. It's something invisible. So this is a huge mystery. This is kind of interesting. This is a pie chart showing the contents of our universe as we understand it today. This little sliver here, this red slice of the pie, which is only 4% of our universe, is what we would call normal matter. This is stuff that stars and planets are made out of, atoms, right? We are normal matter. Our humans are made of normal matter, as is our planet Earth, as is our sun, and so forth. But notice this, what we call normal matter, and this is the part we can understand and explain, is only a tiny slice of what's in the universe. 96% of the stuff in the universe is unknown right now. And this big blue slice here is dark matter. We'll talk about dark energy later when we talk about cosmology and the Big Bang. But dark matter makes up about 80% of all the matter. This stuff here is matter. This stuff over here is energy. All right, but dark matter is about 4/5 or 80% of all the matter in the universe. So what is this stuff? If there's so much of this dark matter, what is it? Well, unfortunately, at this point in time, we don't know yet. This is one of the great mysteries of modern science, and certainly one of the biggest mysteries in astronomy. Some leading candidates for what it could be are small, basically invisible, undetectable black holes. Brown dwarf stars, remember, are stars that are too small to ignite, and they are basically invisible, especially on other sides of the galaxy. We wouldn't be able to see these. Maybe a bunch of rogue planets, Jupiter-sized planets that we just are not aware of. But actually, these candidates here have pretty much been ruled out. Probably the best, the leading candidate at this point are either known or unknown subatomic particles. So these would be particles that are basically too small to be seen, and they don't interact with light in any way, but they have mass, and there would have to be a lot, really a lot of these particles so that they weigh 5 times more than all the other stuff in our galaxy does. So anyway, whatever dark matter is, whoever figures this out and finds out what it is will win a Nobel Prize. So the distribution of dark matter, where is it? Well, they've been able to map this out, astronomers have, by analyzing the rotation curves of galaxies. And it appears that dark matter exists in a large spherical halo around the galaxy. So this is looking at a spiral galaxy edge on, okay, like our Milky Way. Here's the nuclear bulge in the center. Here's the disk, which has the spiral arms, and this is where all the stars, the gas, and the dust are, the stuff that we can see. Around the galaxy are these little spots here. These are globular clusters. Again, these are star clusters of, we understand globular clusters very well. They contain a few 100,000 up to 1 million stars each. But around all of that is this big halo or cloud of dark matter. Whatever the dark matter is, again, we don't know, but it appears to be distributed something like this. Another big question that we have, and we still really haven't been able to answer it very well, is how did our Milky Way form? So the current research suggests that a supermassive black hole formed first and sort of acts as an anchor or a seed for galaxy formation. Again, this is somewhat speculative, though. We don't know this for sure, but we know the existence of these black holes. We'll talk about them more in this lecture later, and also we'll talk about them in part 2 of this lecture. You'll see lots of examples of supermassive black holes. So we know they're there. We're just not 100% sure of their role in the formation of a galaxy, but they may be a key role. They may have acted as a seed. One of the models has a spherical rotating cloud that basically starts to fragment to form the first stars, and we're talking about over 13 billion years ago. So this is a long, long time ago. The cloud then, this is kind of reminiscent of the solar nebula theory, how our solar system formed. Because of this rotation, it starts to flatten out over time, and as it speeds up and flattens out, it forms the disk and leaving halo stars behind. So the disk of our galaxy probably formed about 10 billion years ago. So this is, at this point, really a hypothesis. There is some data to suggest it. However, the hypothesis is certainly not complete, and it's not entirely consistent with observational data. There are some other models as to how galaxies form as well, by putting together parts and pieces to make the galaxy. So this is an area of active research to figure out how our galaxy formed. And the reason this is difficult is because it happened so long ago. So basically, we need more powerful telescopes to look farther out into space. Therefore, we're looking farther back in time to see how the first galaxies formed over 10 billion years ago. One of the important properties and characteristics of spiral galaxies is that there is a lot of active new star formation going on inside of a spiral galaxy. And all this action and activity is happening inside the spiral arms of the galaxy. So this is a really nice image here of a galaxy called M81. And this is a spiral galaxy like our Milky Way. And one thing you can kind of see here is that the spiral arms contain lots of gas and dust. And remember, gas and dust is the material from which new stars form. So inside of these spiral arms, there is a lot of new star formation occurring. New stars are being born and formed. So, and again, the way we can know this is we see two colors that indicate star formation. First of all, the bluish color of the disk and spiral arms out here indicates hot blue type O and type B stars. Remember the spectral classes. O, B, a fine girl, kiss me, right? So the type O and B stars are the hot blue ones. They don't live long, right? They only live a couple millions of years at the most. So wherever we see blue stars in a galaxy, we know they are relatively new. They are not old stars. They're relatively young because they don't live long. And the other thing that we see in the spiral arms is the pink color. That's the hydrogen gas producing pink emission nebulas. And so the combination of the blue and the pink colors in the spiral arms is an indicator that star formation is occurring in the spiral arms and not so much is in the core here or the nuclear bulge of the galaxy. It turns out there's actually not much gas there and therefore not as much star formation. This This is another diagram showing just a little more detail of the structure of our Milky Way. So in the center is a black hole. We'll talk about that shortly. Here is the nuclear bulge of our galaxy. It's actually sort of elongated into what they call a bar. And around the nucleus of our galaxy are several spiral arms that wind out. And you can see that our sun is right here. We're part of what's called the Orion arm, or sometimes it's called the Orion spur. We're sitting between two other larger spiral arms called the Perseus arm and the Sagittarius arm. By the way, the size, if I didn't mention it before, it's worthwhile mentioning it now. Notice that the radius of this galaxy is shown in the scale down here, something like 50,000 light years from the center out to the farthest reaches. So that means the entire diameter of our Milky Way galaxy is around 100,000 light years across. Now that's just an enormous distance. Remember that it takes light a full year to travel a light year. So if you wanted to, if we lived, let's say, over here, and you wanted to send a text message to a friend over here that's, say, 70,000 light years away, well, it will take that text message 70,000 years to get to your friend who lives over here, and if they respond, it'll take another 70,000 years for the text message to return to Earth. So that would be a wait of 140,000 years to hear back from your friend. So you can see that communication across a galaxy is basically impractical. And it's not practical because we just don't live long enough. We don't have enough time to wait for that message to come back. The last part of this lecture, we're going to venture into the center of the Milky Way and explore what's in the middle. The galactic center is located in a region in the constellation of Sagittarius, and you can actually see this with the naked eye. This is kind of what the Milky Way would look like on a summer night or a fall night looking to the south. This galactic center here is in this region right here, but notice that it is completely blocked from view by gas and dust. So you can kind of see these dark clouds here inside of the Milky Way. These are dust clouds, basically. So we aren't able to look at the center of our galaxy with regular telescopes. However, we can use a radio telescope to peer through all of this gas and dust and see what's actually sitting in the center. So this is a radio telescope view, a high magnification, high resolution view of the center of our galaxy. And we see again some gas and dust clouds, but what we're really focusing on is right here. And this is the location of a supermassive black hole, which is basically sitting right in the center of our galaxy. Let's talk a little bit more about this on our last slide. Okay, so in the center of our galaxy sits a black hole, but it's not just any kind of black hole. It is what they call a supermassive black hole. And the mass of the black hole was determined by indirectly by basically watching and analyzing the orbits of stars as they go around this black hole. And so astronomers have been doing this for decades, and they can come up with a precise mass of the black hole which these stars are orbiting around, and it comes out to be 4.1 million solar masses. So think about that for a second. Take 4 million of our suns. Remember, our sun is about 300,000 times more massive than our Earth. So we take 4 million suns and we cram them all into a space that's smaller than an atom. And basically it then disappears, leaving behind a black hole. So this is an amazing discovery, basically, and we're going to find out that other galaxies typically have supermassive black holes, and we'll learn about that in part 2 of this video, which we will do next. I'll see you then.